Hello, this is Jude Socrates, and welcome to a portrait of linear algebra. Our video for today is an introduction to determinants. So we have a very simple goal. We want to learn how to compute the determinant of a 2x2 or a 3x3 matrix. But we are also going to look at patterns and observe how the formulas for a 2x2 or a 3x3 matrix can be extended to a formula for a 4x4 matrix or a 5x5 matrix, and so on. So let's jump right in. For a 2x2 matrix, the formula is very simple. So let's do it this way. If you have this 2x2 matrix with entries A, B, C, and D, the determinant of this matrix is defined by the number A times D minus B times C. So you multiply the diagonal entries together and the off-diagonal entries together, but instead of adding them, you subtract the second product from the first. So other notations for the determinant of A are the matrix symbol A surrounded by these vertical bars that you might think represent absolute values, but no, they don't. And we can also write it as the matrix entries also surrounded by these vertical bars. So instead of using square braces around the matrix to represent the matrix, we replace them with vertical bars to represent the determinant. Okay, so here's a matrix A. What is its determinant? So according to the formula, the determinant of A is 7 times 2, that's 14, minus negative 6 times negative 3 is positive 18, so we get negative 4. Now, if this feels familiar to you, it should, because we actually saw the expression AD minus BC when we saw the formula for the inverse of a 2x2 matrix, if it's invertible. So we said that this matrix is invertible if and only if AD minus BC is not 0. So just a little review. This determinant is not 0, so this matrix does have an inverse. Let's see what it is. Compute matrices and inverse. Yes. Okay, so it does have an inverse. And of course, we said that the formula had the 1 over negative 4. So there's no surprise that there's a 4 in the denominator over here. While we're on the subject, here's a follow-up matrix. So we have this matrix, and now what is its determinant? So this time, 12 times 15, that is 180. Minus 9 times 20, that turns positive, also 180. So of course, that determinant is 0. This matrix is not invertible. Does Maple agree with us? Compute matrices inverse. Undecidable. So that is Maple's way of saying that, no, I don't recognize that matrix as invertible. All right. So we just said that a 2x2 matrix is invertible if and only if the determinant is not 0, as we saw in our formula for the inverse of a 2x2 matrix. So before we see the formula for a 3x3 matrix, let's rewrite the formula for a 2x2 using row and column notation. Okay, so this is A11, A12, A21, A22. So AD becomes A11, A22, and BC becomes A12, A21. So the second term has a minus in front of it. So what are some observations from this formula if you write it this way? Well, there are two terms, and each term has a factor from every row and from every column. Row 1, row 2, column 1, column 2. Row 1, row 2, column 1, column 2. But we wrote down the factors so that the row numbers are in increasing order. Okay? But now, let's look at the column numbers. In the first term, we have 1 followed by 2, so that's 1, 2. In the second, we have 2 followed by 1, so that's 2, 1. The first term has the columns in the correct order, so it has a positive coefficient there, which of course we don't write down. But the second term has the column numbers in the reverse order, or the wrong order. So it has a negative coefficient, okay? So what we will have to do for the 3 by 3 matrix is to generalize this concept of being reversed or being mixed up. And that is the concept of a permutation. We're going to introduce that concept for the 3 by 3, but we will study it in more detail in our next video. Okay, so for a 3 by 3 determinant, let's write out the matrix just like we did for a 2 by 2, where we have the row and the column subscripts. So here we are in row 1, row 2, row 3, and look at the column numbers, column 1, column 2, column 3. So what are some of the patterns and the properties that we will generalize from the 2 by 2 determinant and apply it to the 3 by 3? So I'm not going to tell you yet how many terms there will be. However, there will be 3 factors in every term. Okay, and here we have an advanced screening of what they look like. The 3 factors will have to come from distinct rows and distinct columns. So remember, in the 2 by 2, every row was represented and every column was represented in each of the terms. We will write down the factors though, so that the row numbers are in increasing order. So here is row 1, row 2, row 3. Okay. Now, what about the column numbers? We want every column also represented. Okay. So therefore, we're going to make an example. Let's make 3 for our first column number. Now, if I chose 3 for the first column number, then I can't use 3 anymore for the second factor or the third factor. So I have to use something else. So how about 1? Okay, so I now have a representative from column 3 and from column 1. Let's see, who can I put here? I only have one choice left. It has to be 2, because every column has to appear there. Okay, so now that we have that, we will list the columns as a permutation. Okay, so what that means is that we will just write down the column numbers as they appear. 3, 1, 2. Okay, so those are the column numbers in the order that they appeared in those 3 factors. Okay, so what we're going to do next is we're going to list the inversions that appear in each permutation. So in the 2 by 2, we said, oh, the columns are in the wrong order, the reverse order. Okay, but there are lots of ways to reorder 1, 2, and 3. And I hope you're counting in your head what we did. We had 3 choices for the first column, and then we're down to 2 choices for the second. And then we had only 1 choice left for the third. Okay, so if you write a tree diagram, you'll have 3 choices for the first. Each of those will have 2 choices below that. And then each of those will have only 1 choice below that. So how many permutations or rearrangements do we have? 6. 3 times 2 are 6. Okay, so who are the inversions? What is an inversion? An inversion happens every time a bigger number is to the left of a smaller number. Okay, because we wanted them in the correct order. 1, 2, 3. Okay, well, this one is 3, 1, 2. So the inversions are 3 is bigger than 1, and also 3 is bigger than 2. Okay, so it doesn't matter that 2 is not right next to 3. All right, it is still to the right of 3, further down, and 3 is bigger than 2. What about 1? No, 1 is not bigger than 2, so 1 does not contribute an inversion. Okay, so now, what are we going to do with these inversions? We're going to count them. Okay, so obviously there are just 2 inversions in that permutation. Okay, so what is this going to do to the formula? If the count is even, that term will have a positive coefficient in the determinant formula. If the count is odd, the term will have a negative coefficient. So our final term is just going to be A13, A21, A32, contributing positively. Okay, so we're going to repeat this process for the other 5 permutations of 1, 2, and 3. Okay, so I mentioned 1, 2, 3. Okay, if the columns are already in the correct order, there are no inversions, so you have 0 inversions. 0 is an even number, so the coefficient of A11, A22, A33 is positive. A11, A22, A33. Okay. How do you list down the permutations in some organized way? Well, one way to do that is to keep the leftmost number as long as you can and change the other orders, the other numbers rather, to the right. Okay, so you have 2 ways to fill in the second and third number. So you keep the 1 and you write the second order 3 and 2. Okay, there are no more permutations where 1 goes first. So now we start with 2. Okay, so you're left with 1 and 3 because you've used up 2. So the permutations left are 1 and 3 here, and 3 and 1, the reverse order. So finally, you have 3 to start off your permutation. You're left with 1 and 2, which you can order that way or as 2 and 1. Okay, so let's look at the inversions. 1 is not bigger than any, 3 is bigger than 2. So that's the only one. 2 is bigger than 1, but not 3. 1 is not bigger than 3. So there's 1 inversion also. 2 is not bigger than 3, but 2 is bigger than 1. So that's an inversion. 3 is bigger than 1. That's another inversion. So this has 2 inversions as well. The next one is what we just did earlier. So these also have positive contributions. Last one, 3, 2, 1. 3 is bigger than 2. 3 is bigger than 1. And 2 is also bigger than 1. So there are 3 inversions. And of course, this is the exact opposite order as 1, 2, 3. So this will have the most number of inversions. But since there are 3 inversions, it will have a negative coefficient in the formula for our determinant. So notice, I hope you notice, that you have 3 positive terms and 3 negative terms. That's not an accident. And we're going to learn that in the 4x4, 5x5 formulas, that pattern will also continue. So in this diagram, I listed out those 6 terms. And what I did was I copied our 3x3 matrix and I boxed in the factors in each term. This tells us, we can see right away, that every term has a representative from every row and from every column. And there are 3 of them which are positive and 3 of them which are negative. All right, so we can now formalize our computations earlier and create the determinant formula. Okay, so these are the 6 terms that we had, our 3 positive terms, followed by our 3 negative terms. Now, here is a nice mnemonic, a way for you to memorize this formula. In fact, you don't even have to memorize it. Okay, all you have to do is copy the first 2 columns in your matrix to the right. Okay. Who are the positive terms? 1, 1, 2, 2, 3, 3. Okay. And then we have 1, 2, 2, 3, 3, 1. 1, 2, 2, 3, 3, 1, because 3, 1 was over here. Last positive term, 1, 3, 2, 1, 3, 2. Okay. The negative terms are found in the reverse direction. Okay. So if you like, you can start on the right this time. So you have A1, 2, A2, 1, A3, 3. 1, 2, 2, 1, 3, 3. That's this last term here. So it has a negative contribution. 1, 1, 2, 3, 3, 2. That's this term. 1, 3, 2, 2, 3, 1. That's this term. Okay, so you multiply these together, put a plus sign in front of them. These together, put a minus sign in front of them, and then add all 6 terms together. So let's find the determinant of this 3 by 3 matrix. Okay, so the mnemonic said, let's make a copy over here. Copy the first two columns to the right. Okay, and then we will multiply the entries together going to the right. 9 times 3, 27, positive contribution. 4 times 8 times negative 2, I believe that's negative 64. So you can write it as plus negative 64 or just minus 64. Okay, next one, you have 2 negatives, so that is positive. So 21 times 5 is 105. So that's going to be plus 105. Okay. Now backwards. 7 times 4 times 1. So minus 28. And then, there's a negative there. So we have, let's see, 40 times 3, 120. Minus 120. Minus 120. Those negatives, they just trap you. Last one, we have 2 negatives, so those cancel, but you have a negative in front, so you have a minus there, and you're going to get 27 times 2 is 54. Okay, so you add that all together. I'll just click equals here, 106. Okay, and speaking of clicking, I can just highlight that, compute matrices, and of course, we do have a determinant function in Maple, 106, right? So of course, that is the correct answer. Now, spoiler alert, we said for a 2 by 2, a 2 by 2 matrix is invertible if and only if its determinant is not 0, okay? So this determinant is not 0. Is the matrix also invertible? Well, let's ask. Compute matrices inverse. Aha, yes. It is invertible. Ooh, there's a 106, and we'll wonder where that came from. I guess we'll never... Of course, there is a formula for the inverse of a matrix that takes the reciprocal of the determinant. Okay. So let's do a follow-up actually. Okay, so we did 2 matrices for 2 by 2, and we saw, okay, the second one, the determinant was 0. Okay, so you know what, let's turn that into positive 5. Let's repeat that 1 and, negatives. Let's square it so that it becomes positive 4. Okay. So there you go. I just did some random things over there, little upgrades here and there. So let's ask Maple. Compute matrices determinant. Okay, so we can of course do what we just did for our original matrix, or you can try that yourself. Oh, this is so much easier. The determinant is 0. Okay, so if our suspicions are correct, then this matrix should not be invertible either. Compute matrices inverse. Again, Maple says, that matrix is not invertible. Okay, so obviously this is a property that we will prove later down the road, that a matrix is invertible, a square matrix of course, is invertible, if and only if its determinant is not 0. There's a second property of determinants that is also very important, and we will prove it as well. I'll tell you what it is. The determinant function turns out to be multiplicative. Okay? Again, we're used to additivity properties. Okay? Although we did mention, I hope you remember, it wasn't just a video or so ago. I believe it was in the last video actually. We said that the set of invertible n by n matrices is closed under matrix multiplication. If you multiply two invertible matrices, the product is still invertible. Okay. Well, this example, even though the determinant is 0, okay, it's not very interesting for what I want to show you. Okay, so maybe I'll bring this back to 1. Okay, is that a more interesting determinant? Compute matrices determinant. 10. Okay, that's more interesting. Okay, so if you believe what I just said, okay, what did I just say? It turns out that the determinant function is also multiplicative. Okay, so what does that mean? Here is a matrix A. We found the determinant to be 106. Okay, let me erase this. Here is a modified version of A. Very different determinant. It's now 10. Okay, all right, so what are we going to do? Let's multiply these two matrices together. Okay, so we can multiply them in that order, and we will get, nasty. Okay, well, but we have a computer, so compute matrices determinant. Okay, so what did we say? The determinant of that product should be the product of those determinants. And that's really a lucky outcome that that second matrix simply has determinant 10. 106 times 10, that's easy to do. Do we get 1060? Bonus example. We said that matrix multiplication in general is not commutative. Oh yeah, completely different product. There's a 50. Oh, look, these two entries are the same. Not much else. All right, however, if you believe what I said about the determinant, then the determinant of this product should also be the product of the determinants of these two matrices. Oh, but wait a minute, that's 10 and 106. This should also be compute matrices determinant, of course, 1060. So even though the products are almost completely different, they do share one thing. Their determinants are exactly the same. Okay, so that is our video for today. As usual, you will find me on Facebook, and you will find the 4th edition on Facebook and at kendallhunt.com. So until our next video, when we talk about permutations and their properties, I hope you enjoy the rest of your day.